These are going to be the math examples for your conservation of energy notes. So let's say a 4.5 kilogram box is lifted to a height of 2 meters. Things we know, we should get in the habit of still labeling things. A height of 2 meters were then dropped. How much kinetic energy would it have as it hits the ground? And since it's hitting the ground, I'm going to say that's the kinetic energy final, how much energy it has at the end of the motion. So normally, if you're solving for kinetic energy, you would use this equation. And we do know the mass of the box, but we don't know the velocity. So I'm not going to use that here. But I have another equation I can use. It's that long equation, which doesn't seem like a good idea to use, but it's actually extremely helpful. After the box is lifted, it has gravitational potential energy. It has a height, but is that box moving? The initial velocity of that box is 0. So I know it doesn't have any kinetic energy. But I do know that as the box falls, it gains kinetic energy. So I am going to use that conservation of energy equation. And I'm going to write how I come up with the equation. You do not need to write these steps every single time. Eventually you'll get into the habit of just writing the shorter version of it. But the total mechanical energy the box starts with has to equal the total amount I end up with. That's that law of conservation of energy. So I know kinetic plus potential that I start with has to equal kinetic plus potential that I end up with. I know at first it's not moving. So I know my kinetic energy is 0, so I can immediately shorten that equation. I know it has kinetic energy at the end, and that's what I'm looking for, so I'm going to leave that alone, but its height as it hits the ground is 0. So that means the gravitational potential energy as it hits the ground is also 0. So I can shorten this equation. Basically, the gravitational potential energy I start with has to equal the kinetic I end up with, which you kind of already knew from the previous conceptual video. Here's the trick. I am looking for kinetic energy final, so I'm not going to replace this equation with its little individual equation. But I do know mass and height, so I will use the equation for gravitational potential energy. So mass times gravity times height will give me kinetic energy final. So now I just plug in stuff I know. When I plug all of that into my calculator, I get 88.2 joules, which I would round to just 88 to keep proper sig figs. You won't always be able to cancel out energies, but you can. And you should definitely pay attention to when an object isn't moving or when it's at the ground level, so you can make this giant equation simpler. So let's look at another scarier example. A swing is lifted from its original position and release. It is moving at 2.9 meters per second as it passes through the lowest point, we'll say that's about here, of motion. How high was it lifted from its original position? So this is like an example of a pendulum, which maybe we've talked about in another video or you've seen in another place. But the object swings back and forth, and I know at the very ends of the motion, the swinger is not moving. At the very lowest point, her height is 0 or smaller than the highest point, but she's probably moving the fastest at that point. So I can use conservation here. Total amount of kinetic that I start with plus gravitational potential that I start with equals how much I end up with. And you could pick any point in the motion for the initial and the final. For this problem, I'm going to say initial is when she was lifted, and I'm going to say the final is down here at the bottom. So I know at that initial position, she was kind of dropped. At first, she wasn't moving. So I know the kinetic energy is 0. And I know at the lowest point compared to the highest point, she doesn't have a height. That's the lowest point in the swing's motion. So I'm going to say gravitational is 0. So the simpler version of this equation is the amount of potential that I start with equals the amount of kinetic that I end up with. This problem doesn't seem like it gives me that much information. I only know the velocity at the lowest point, which we are saying is the final velocity. So I'm going to go ahead and write out this equation because this seems kind of scary. It's 1/2 mass times final velocity squared. If I go ahead and plug stuff in, you're going to see that I'm missing something. I am looking for my height initial, and I know my final velocity is 2.9, but this problem does not tell me the mass of the swinger. But look at what I just wrote down. Do I need to know the mass of the swinger? What do you notice is on both sides of this equation? The mass. So if I try to move all the masses to the same side, I end up dividing by itself, and it ends up canceling out. So really simple, all I have to do from this point is to move 9.8 to the other side and plug this into my calculator. And so I get the height initial is 0.42 meters. So if you notice in this big long equation, I have room to write it down here. If I write out the whole thing for this equation, 1/2 mass times initial velocity squared plus mass times gravity times initial height plus the same thing on the other side. What term or what letter do you notice is in every single piece of the equation? Mass. So if I'm solving for velocity or height, I don't really need to know the mass because it cancels. But sometimes problems will ask us to solve for energy. And since both kinetic and gravitational potential depend on mass, if I'm looking for energy, I cannot cancel out mass because mass makes up each of these types of energy. But if I'm looking for velocity or height, I can cancel out the mass to make it simpler. It doesn't matter if you do cancel it out, it's just an option if you want to. And maybe this reminds you of an older unit. When you are solving for final speed as you drop an object, did that depend on mass? It didn't. This is